All right, so here we're going to be doing an exercise, an example problem, where we have a velocity already broken into two components. So u is equals to negative y and v is equals to x. So we can find our stream function um, that is psi is equals to u dy and psi is equals to negative v dy, and we have to add these two together. So here we get what is u in terms of y, negative 1 half y squared, and here we get negative 1 half x squared. Okay, so now we put this together, we get 1 half y squared minus 1 half x squared, and this is our psi. So now the thing is, we can take this and put it equals to a constant, because psi will be a constant. Okay, so now I want to get rid of the negatives, and I have 1 half y squared plus 1 half x squared is equal to negative c, but just c, so we just say c again, it doesn't matter. Our constant can be whatever we want, so we put a negative in front. You want to affect this, then multiply both sides by 2, so y squared plus x squared is equals to 2c. Again, it's our constant. If you multiply by 2, it's still going to be a constant, a random constant, so it's just going to be c again. So now we've proved that our stream function is just a circle, a concentric circle with radius. Um, well, this is going to be the radius, technically speaking, because when we're trying to find the radius, we're going from Cartesian to polar. We would have to take u squared plus y squared, and we would just get um, is it well, we have negative y squared, so y squared plus, oh, u squared over here, plus x squared. So the radius is equal to square root of y squared plus x squared. Okay, so since we have a rotation around a fixed radius, then we have a solid body rotation. Remember, we're rotating, we're not changing the dimension or anything. The dimensions do not change because it's just a circle. Um, so we're rotating around a circle. Now we can evaluate the contour integral, and we can do this in two ways. I'll do it in both so you can see it. So first of all, we can find the vector. Also, I want to say, let's start this. Okay, so our this is going to be equals to the curl of our velocity vector. So it's equals to, let me bring this down a bit. I, j, k, dx, dy, dz. And then we have negative y, x, and z. So we know it's going to be just in the k component because it has to be perpendicular, and our u is in the xy plane. So we're just going to get 1 minus negative 1, that's equals to 2k hat. So we would have to do this. So the integral over surface, our vector will be that double integration times n hat times the area. Um, so we can say that R is going to be the area of a circle. So we just say the integral s 2k hat dot product with the k hat vector because it's the area is on the xy plane dA. So I get this out 2 surface integral of 1 dA. Well, the area is just going to be the circle size, so 2 pi r squared. Uh, and of course depends on whatever r is. Now we can do the same thing with our um, other method, which says that it's going to be the integral over a closed surface of u times dl vector. Oops. Okay. So now, since we don't have movement in we have movement in Cartesian coordinates, that become just complicated and hard to do. What we can do is move it to polar coordinates. Um, so we can say that our u hat vector is going to be our radius in the direction of the angle. So yeah, and dl, well, it comes from the area of a circle, or it will be a vector as well. It'll be r d theta in the direction. I want to prove this first of all, so we know that dl, if we were to take dl and we go from 0 to 2 pi, because we're taking an entire circle, and then we're also going from 0 to r. Okay, so we get 0 to r, 0 to 2 pi, r d theta vector. Okay, um, so we get well, first of all, integrate for d theta. Theta doesn't exist, so we're just going to be at theta, and then it goes from 2 pi to 0, so just 2 pi, so we get 2 pi r, which can remind you of the circumference already, and then we integrate over r, so we get 1/2 r squared, and of course the 2 pi in front, I'm going to put 2 pi, and 1/2 r squared from 0 to r equals to 2 pi 1/2 r squared. We simplify the 2's, and we get pi r squared. Okay, well, another way you could have done it is by starting from the area of the circle, pi r squared, which is known. Derive this in terms of either r or theta, doesn't matter which one you want to do first. I'm going to start with r, so we get 1, so we get 2 pi r, and then I would have to integrate this, sorry, to derive this in terms of theta. Technically speaking, we get 0, oops, 2 pi r d theta. But we get 0 because there's no component, in fact, in the theta direction, but we know it goes from 0 to 2 pi, so the 2 pi comes from here. And then the r is just going to be the initial value. So we'll just, technically speaking, so we just come, oops, this comes from theta, so we can just get r. All right. Okay, so after we went down this rabbit hole, we can plug in here. We get r in the direction dot with r d theta and the e theta hat or a closed contour. And a closed contour we said is from 0 to r, from 0 to 2 pi, 0 to r, from 0 to 2 pi. So we get, well, actually r in this case is already given to us. So it's the velocity. So we just have r squared d theta, which ends up being 2 pi r squared, which is, oh, it was right here, the same answer that we got from the first one. So this is our equation. We're proving the different ways to prove that we get the same result. Of course, if we were to take the unit circle, it would just be 2 pi, because the radius would be 1, but that's just an additional thing.